Hey guys, Mr. Betts here. I want to take a look at a couple examples where we are writing the Maclaurin series for a function, and we're going to use a little bit of a trick to do that. So it's a trick that we've talked about already. So first of all, if we were going to write the Maclaurin series for this particular function using the traditional method of taking derivatives and plugging into the function, we would get some really messy derivatives. So the first derivative using the quotient rule, we would get right here. And then the second derivative, after we clean that up and use the quotient rule, we get right here. Taking a third derivative, as you can imagine, would be really, really annoying. And then we would plug in, since it's a Maclaurin series, we'd plug 0 in. And it turns out that the function at 0 is 0. The first derivative is 3, second derivative is 0. And if we were to keep doing this, the third derivative would also be 0. So as messy as this is, the second derivative would be 0. If we clean that up and do the quotient rule, that's going to be even more of a mess, but we would get 0 for that. Seems a little frustrating that we're getting zeros for all the work that we're doing. And then finally, again, on the fourth derivative, we'd get a non-zero number, and then we'd have to keep going from there. So as you can see, this would be a really messy process if we were trying to do this the traditional way. But if you notice, this function is written in the form of the sum of a geometric series. So remember, the sum of a geometric series is the first term over 1 minus the common ratio, as long as the common ratio is between -1 and 1. Well, if we look at this function here, we can think of the numerator as the first term in a geometric series, and we can think of this 4x cubed as the common ratio in a geometric series. And so what we can do is we can build our Maclaurin series using that. So the Maclaurin series for this is going to be the first term, which is 3x, and then we're going to multiply by the common ratio over and over again. So we're going to take that 3x and we're going to multiply it by 4x cubed. That's going to give us our second term of 12x to the fourth power. Then we multiply that by 4x cubed. So multiply that by 4, we get 48. And then times x cubed is x to the 7th. Then we multiply that by 4x cubed. So I think it's 172x to the 10th. And so on. So the and so on, we can write the general term as the first term times the common ratio to the nth power. Okay, so this term here is 3x times 4x cubed to the 0 power. If we plug n equals 1 in, we get this one, n equals 2 in, we get this one, and so on. So we get this Maclaurin series for a function by using a geometric series. Now, if we do that, we also want to keep in mind that this is only going to be the Maclaurin series for this function on an interval. And that interval is going to be when the common ratio is between -1 and 1. So what that means is this series will only converge for values where this inequality holds. We can solve this inequality by dividing by 4 on both sides and taking the cube root. So let me try that again. So this is actually a pretty small interval of convergence. It's only going to converge for this interval right here. But on that interval, this Maclaurin series that we just wrote is equal to the function. Looking at another example here, this one's a little bit tricky. We have to be careful with one like this because the sum of a geometric series is the first term over 1 minus the common ratio. And what's really important here is that this is a 1, and we don't have a 1 here. Now, that doesn't mean we're just going to give up, but what we can do is we can manipulate this function a little bit by dividing the top and the bottom by the same thing. So I'm going to actually multiply it by 1/3. So if we multiply top and bottom by 1/3, this function is going to be 5/3 x cubed over 1 plus x squared over 3. So now this is in the form of 1 or the first term over 1 minus the common ratio. And actually, to make it even more in that form, that plus in the bottom, I'm going to write as minus negative x squared over 3. That way we can see then that the 5/3 x cubed is going to be the first term, and the negative x squared over 3 is going to be the common ratio. So using that to build our Maclaurin series, we're going to have the first term, and then we're going to multiply by that common ratio over and over again. So since it's negative, that's going to make the terms alternate. Multiplying by x to the, multiplying by 1/3, we're going to have 5/9, and then times x squared is x to the 5th. Then multiplying again times the negative is going to make this positive. 5 over 27 times x to the 7th. And then minus 5 over 81 x to the 9th. All right, and then for our general term, again, we're going to take that first term, 5/3 x cubed, and we're going to multiply that by the common ratio to the nth power. And there's your Maclaurin series for this function. The question didn't ask for it, but also keep in mind, I'm going to write down, I'm not going to solve this, but this is only going to work if the common ratio is between -1 and 1. So we would need to keep that in mind. Actually, let's go ahead and solve it just to make sure that we know how to do that, because that is something you should be able to do. I'm going to multiply both sides by -3. And remember, when we multiply, that's going to flip the inequality. So multiplying by -3, we're going to get 3 is greater than x squared is greater than -3. Then we're going to take the square root. Taking the square root doesn't change the inequality, because the square roots of bigger numbers are bigger and smaller numbers are smaller. So we're going to have the square root of 3 is greater than x is greater than the square root of -3. Now notice what we've got here is that x is greater than an imaginary number, so we can ignore that part of it. And so this is only going to be true for x values that are less than the square root of -3.